Manuel Chakravarty. Yeah. Manuel received his PhD from the Technical University of Berlin, and then went on to become a faculty member at the University of New South Wales in Sydney from 2000 to 2017. He has since left academia to become a functional programming evangelist at Twig.io, and more recently a blockchain language architect at IOHK. Manuel has long been a fixture of the functional programming community. He served as general co-chair of ICFP in 2011 and program chair in 2014. He's well known for his work, often in collaboration with Gabby Keller, on, among other things, Data Parallel Haskell, the Haskell for Mac development environment, and GHC's type families. His work on associated types, which was published in ICFP 2005, received the most influential paper award 10 years later, and has had impact on other programming languages as well, including Rust. On a personal note, I just want to add that I'm very happy to be introducing Manuel because he really had a big impact on my life. After I had just got my PhD from Carnegie Mellon in 2005, I was looking for new research projects, and I met Manuel and Gabby at ICFP, where they were presenting the associated types paper. And I thought that had interesting connections with ML modules, which was my thesis topic. And that led to my first collaboration with anyone outside of CMU. And not only was it a successful collaboration, it was a very warm and engaging human interaction that actually gave me the confidence that collaborative research was something I wanted to do. So thank you for that, Manuel. And please join me in welcoming Manuel Chakravarty.
Good morning. Welcome to ICFP 2019. And as you may know and just heard, I used to live in Australia for a long time. So at conferences, I tended to be one of the most jet-lagged people in the room. Now that I've moved to Utrecht and ICFP is in Berlin, I'm actually awake. So first of all, I like to thank the program committee for giving me the opportunity to speak here. It's a great honor. ICFP has always been my favorite academic conference, so it's really an honor. And what I want to do, I want to tell you a little bit about what I've done the last 1.5 years. When, 1.5 years ago, Phil Wadler, who's sitting over there, asked whether I would be interested in working on the Plutus project, doing smart contracts for some blockchain. And I didn't know too much about blockchains. I had done a little looking into it. And it turned out over this time that actually blockchains, functional programming goes so well together. And that's really what I'm going to try to communicate today. So let's start with the basics. So what's this like? Of course, blockchain is in all kinds of media, stories and hype, but we are not interested in this, right? We want to know what's the technical core. Why is that interesting? How does it relate to functional programming? But to understand that, we have to see where this idea comes from. So let's just assume 3 people, crypto, it's always Alice, Bob, and Charlie, and they have funds in their local wallets. And then maybe they want to exchange those funds, do some transfers. But if they just keep tally of their own accounts, then, I mean, they could be cheating, right? So the standard solution is, well, get a bank. And then instead of keeping the tally themselves, they just tell the bank, which keeps accounts in their name. And that's all good and well, but we see already at this point now, ordering becomes an important issue because what if we have a message a little too early before the transfer from Alice arrived, and now we have an invalid situation. Also, can we trust this bank? Maybe Charlie is a really good hacker, and he manages to empty all the accounts. Well, in Western banks, maybe we rely on they will pay us out anyway, but that's not the case everywhere. So the idea, the technical, logical idea here is to, let's suppose we have a data structure which we all can agree on. This is where the consensus bit comes in, and I'm going to talk about this a little bit more later. And then instead of updating things in place, now at that point you should should agree with that this is a good idea. We just add something to the data structure. We don't modify it. We just incrementally extend it. And then it's immutable. Isn't that great? So we have this immutable, verifiable, due to the cryptography, ledger data structure. So maybe it seems like a waste to only use that to store information about monetary values. We could add some more information. In the simplest case, we could just say, okay, we can attach some metadata about what these funds, these transfers were used for, why were they done in the first place. That's not much more interesting. Let's try something bigger. So multiplayer computer games are very popular, and if you know games like Fortnite, Team Fortress, this kind of stuff, then people typically they have some in-game artifacts which they get for particular achievements, and then they can trade them. And they're actually markets, online markets, where people like crazy trade these items. Some of them become really expensive. And now this sounds like the perfect application for blockchain. But then things get more complicated because now suddenly we have this additional information and we have to make sure it's also consistent. So maybe Alice runs the server, Bob gets a fancy hat because he had this great achievement, and we have to record this on the ledger, this information. And if Bob wants to trade this hat later on, then the ledger has to make sure that this trade can only go through if Bob actually really received this, this hat. So we need some additional validation logic to ensure the consistency of the ledger. And that's where it starts to become interesting, because now we need some application-specific code, which is kind of part of this validation procedure. But that's not enough, because we have to hook this data structure, the ledger, up to the bigger game system as well. So we need some out-of-the-ledger additional code as well. So now we need a programming language, which people call smart contracts. But think about the smart like you think about your smartphone. It doesn't mean it's particularly smart, only that you can run code on it. Somehow some people think only because you can program something, it becomes smart. I don't understand it. Now you may think, okay, cute, but games, is this going to change the world? Well, let's ask the European Commission. So the European Commission has this strategy point at digital single market, and they are also investigating what blockchains can be used for in the context of the administration of the European Union. And they have quite a few interesting applications: identity management, management of health records, even tax proceedings. So that seems a lot more serious than computer games. So there are all kinds of applications. It's just that this fancy hat thing is easy to explain. All right, so let's assume this is interesting. We can actually do interesting applications with this kind of data structure. We all agree on what's on it. Then let's look at what we would need to do this and where the difficulties are, because the idea is quite simple. Execution, not so. So we have two types of code. We have the on-chain code, which is used as part of validating these new transactions, which get onto the ledger. And then we have the off-chain code. And these two pieces of code, they run on different computers. The validation code has to run while the ledger is constructed on the servers which construct the ledger. Whereas the off-chain code, connection to the video game I'm playing, that has to run on my computer. Okay, so we already have two computers here, distributed system. Unfortunately, it gets worse. So we have to add this validation code to the ledger as well. So now we don't only just store data on the ledger, we have to store code on the ledger, on this immutable data structure. Why? Because otherwise somebody who comes in later couldn't replicate that this ledger was actually properly constructed and do all the custom validation. And then, unfortunately, it's a highly distributed system because we have lots of servers and lots of clients with wallets of users. And all this stuff has to work together. Now, the clients, that's not so different from a situation with the web server and web browser. So that's not so difficult. But these many servers, that's where it starts to get really tricky. Because all these different servers, they have to agree on what is the one true ledger. And for this, we need something called a consensus protocol. And there are basically 3 ways, generally speaking, we know how to do this. So number one, this is what Bitcoin does, is to use something called proof of work. Now, this is unfortunately very wasteful, because what these servers called mining nodes do, they solve pointless cryptographic puzzles, spending a lot of energy. And the fact that they can spend this energy is indirectly used to construct a proof, and this has been properly proven, that nobody can easily replicate it and falsify it. But it's very wasteful. And we just heard about how ICFP, which is really awesome, is carbon neutral. This is certainly not carbon neutral. So that's not good. The alternative is something called proof of stake. In proof of stake, the proof for the consistency of the ledger is not by pointlessly wasting energy, but by the people who have an incentive in keeping the system running, namely those who are invested, who have cryptocurrency on the chain, deciding in a kind of democratic way who's producing blocks. Unfortunately, this is way more complicated to construct a good protocol for it and be proof that this protocol actually has the same security properties as that of Bitcoin, this wasteful proof of work protocol. But there's good news. The research in cryptography is now at a point, or for a while, that we can implement these kind of systems. And I'll tell you how in a second. And the third one is to have what's called a permissioned ledger. This is not really a public blockchain, but actually a consortium of, say, companies saying, OK, we tell you if you can run a server, you have to get permission from us. So it's actually a closed system. But it's important because it's been in the news recently. And we'll get to that. So this interesting case is really the public blockchains and these consensus protocols. And this is still a very active research area in cryptography. Lots of paper being published on how to do this kind of thing better. But it's also something you have to really get right. So the market capitalization of Bitcoin is something in the order of 160 billion at the moment. So there's a very high incentive for people to hack the system because there's a high payoff. And these algorithms are really, really complicated. So that's a problem, right? We have this complicated algorithm. We really have to implement it properly. And really, the protocol has to be good, too. And then you may think, well, why don't we do away with all this cryptocurrency nonsense and just focus on the data structure and the interesting use with additional data? That doesn't work either, because in a public blockchain, it's the monetary value of the cryptocurrency which incentivizes people to run the servers producing the chain in the first place. So having a cryptocurrency in a public blockchain is needed by not just design, but principle. And the incentives around distributing this cryptocurrency is one very important part of the design of a blockchain in the first place, of a public blockchain. So we are kind of stuck. We need this. That means we have currency, which means people want to steal it, which means you really have to get it right. So we are in a little bit of a tight spot. So let's summarize. So it's kind of, I hope I've conveyed these distributed consensus-based data structures, well, interesting applications maybe. And we can use programming languages to great effect because we have code on the chain, code off the chain, how we organize this, well, who knows. And there's a sustainable way of having these protocols too. And we really have to get it right. So we'll better write some proofs about what these protocols do, that they actually work, and then have a way to implement them in a way which is better than just hacking something and testing it on 10 examples. OK, so having said that, let's look at the architecture of a blockchain and which bits are most interesting in the context of functional programming. So at the bottom, we have what's called the network layer. That's quite standard networking. And yeah, the We can do interesting network things in functional programming, but that's not the most important part. Then the consensus layer, this is where these protocol proof of work, proof of stake are implemented. We really have to get this right. So we really want to use proofs, formal proofs, if we can actually fully verified implementations. At the ledger layer, which are the rules about which transactions are permitted, so I can't deduce from an account if it goes into the red. That's less complicated logic, but also something we have to get right, because obviously otherwise the accounting doesn't work anymore. And then the real playground for the people in this room, this is the contract layer, where we have a programmable system on top of the blockchain and what people call programmable money. So that's something domain specific. Now, taken together in the consensus and ledger layer, we can use a lot of work on formal specification, formal methods, verification using type systems to help us get the implementation right. A lot of good testing strategies like property-based testing. And on the contract layer, we can use all the nice technology which is being presented in this room throughout the next 3 days. Certified compilation is very interesting. Again, we want formal methods and so on. All right, so given this situation, given the high stakes and the need to get it right and to have something like a high assurance, rigorous approach to this, and given that even designing the protocol is something which is hard and still an active research area, you might think there should be some blockchain protocols out there who've taken this to heart and said, yeah, we want to do it right. Not just hack a system together, design it properly. And yes, there are. There are actually a few. So I just want to give you a bit of an overview there. First, with respect to implementation of the system itself, we have the Eternity chain, which is implemented in Erlang. Then there's Cardano, which you'll hear more about later on, implemented in Haskell and Rust. Concordium is a new one, which is a spin-off of the University of Aarhus. And they are using Haskell, Rust, and OCaml. Then Libra, which was in the news due to involvement of Facebook, is implemented in Rust. Then we have the Tezos project, which is done in OCaml. And Silic, which they implement in C++, the chain. That's disappointing, but at least on the smart contract layer, they're working with OCaml. So that's the programming language side. But then on the proving side, obviously Coq wins. And this is for both reasoning about protocols, reasoning about the implementation of the protocols, and reasoning about smart contracts and the implementation of those smart contract tools. So in all these domains, various forms of formal methods are being used, and dependently typed approaches are definitely the most favorable contestant here. The Libra folks claim they're going to do something about formal verification, but they haven't shown anything yet. So that's why I'm saying to be announced. OK, so how about smart contracts? So Eternity has an OCaml-like language called Sophia. We've decided to just stick with Haskell, not invent our own programming language. Concordium has Oak, which is an Elm variant. And the Libra folks use a new language, but it has a linear type system and is kind of semantics is fairly functional, let's put it like that. And then Tezos has OCaml-based, OCaml derivative, and Celia is also a new functional language. So there is all this work. There's quite a lot of work in the functional programming and formal methods domain in this area. And then there's a few languages which are higher level, independent of particular blockchain. There's the work by Fritz Henglein's group on contract specification language, the work by Digital Asset, who are, I think, also sponsoring this conference. Marlow is based on the ICP 2000 paper by Hayden Jones, Hebert, and Stewart on financial contracts in this blockchain version of that, done by Simon Thompson. And there's the work on simplicity. So there's quite a bit, if you're interested in this area, there's quite a bit of stuff to look at and read. OK, but as I promised, I want to talk a little bit more about Cardano and what we are doing there. So first of all, Cardano is a proof-of-stake blockchain. We don't try to kill the planet. There's very heavy use of functional programming in the implementation of the chain itself, as well as with respect to smart contracts. And it's a very research-driven project. The premise of the project was we really have no idea how to do this properly. So first of all, we need a lot of science. And then we can implement that. So not surprisingly, IHK has started the Blockchain Technology Lab at the University of Edinburgh, which is headed by Aggelos Kiayas, who is also chief scientist of IHK. And his research group developed the so-called Ouroboros, a proof-of-stake protocol, which is the basis of Cardano. And Phil Wedler is also involved in this lab and is the leader of the programming language area. And there are all kinds of other universities involved as well as collaborators. So there's a really very strong basis in let's do this properly, let's do the science first, and then let's get it right. But this immediately leads to a problem. So now we are designing these cutting-edge protocols, which are quite complicated, and then somebody has to write some Haskell or Rust code, which hopefully does the right thing. So how do you get from one end to the other? That's a difficult problem which all kinds of companies, universities, research groups have tried to tackle. So here a little bit about IHK's take, because it's very heavily based on using functional programming. So where we want to go from the latest research papers to production code, and we do this via the use of formal methods. So it starts with a research paper, something like the Ouroboros protocol specification. This is the first Ouroboros paper, but there's a whole sequence. Things like sidechains, which is another way to improve scaling of blockchains, or the Marlowe paper on financial contracts using functional programming. That's great, but then how do we do the next step? We have this paper. Well, first step is to write a semi-formal specification. So this is something which everybody in this room would look at and immediately say, oh, yeah, clear. It's basically set theoretic-based equations, which in this case describe how the wallet backend of the blockchain works. And then we take this code and we translate it into Haskell. Now, if we take this operation running on a pair, and we translate this into Haskell code, well, there's some state handling in there. Instead of a pair, we use a record. But for somebody who knows Haskell, who can read this mathematical notation, pretty clear these two things do the same thing. It's not a formal proof, but it's a translation of the formal specification into something which quite clearly does something like the specified thing. And the same for the functions being invoked in the specification. We also have a set comprehension here, which we then translate into corresponding collection-based operations. OK, so now we have an implementation which corresponds closely to the specification. Unfortunately, very slow, because it's really just a translation of this set-based specification, so that we can't use that in production. So then the next thing is to take this as a prototype and on the basis of that, write a second implementation where we do all the hard things. Okay, we have to get networking. Then blockchain can roll back to a certain degree. We have to construct the chain incrementally. We have to persist the data to disks. All these stuff. So then we have the real production implementation, and we have our prototype. And when we take John and ask him for advice about how could we test the two against each other, please? And he's going to tell us, property-based testing, of course. Haven't I told you that all along? And in this way, we can get a high assurance of our production code doing the same thing as the prototype implementation, which in turn we are quite confident does the same thing as the specification. So in this way, we gain high assurance, even if we don't have full formal verification of the code itself, because that would be really hard to achieve in the time frames where at some point we have to actually deliver code, otherwise people won't be interested anymore. Okay, but the point here is functional programming, and the kind of approaches which we've been telling people to use are really at the core of this development process. And Duncan has a nice video where he explains all this, if you want to get more detail. All right, so let's get to the smart contracts, whether they're smart or not. So let's start with the ledger, the data structure. How can we make this more functional? Because really, if you look at this, adding transaction to the set of accounts and then telling up who has what, this is sounds like an imperative approach. I mean, maybe in your first lecture on object-oriented programming, people like to use this. Imagine you have accounts and messages, transfer money. It's not, it's very imperative object-oriented view of the world. But let's imagine we had something more like banknotes. Okay, so the participants, they have these banknotes in the beginning. Alice wants to pay Bob, but not 100 ADA. So she splits the note into 2 notes and gives the 42 ADA to Bob, who then combines it with his 10 ADA to do the second transfer to Charlie. Now, in this model, it's the ability to spend any of these dangling bits in this graph which conveys the ability to, or conveys ownership of those funds. Now, this structure, because it depends on these not yet spent bits of the graph, is called an unspent transaction output graph, also UTXO graph. And this thing was actually underlies Bitcoin. So this was invented in context of Bitcoin, and it's a way more functional representation. It's really data flow graph, right? So that's great, and we have a paper about the correlation between these 2 models and how you can simulate one in the other, so they have this similar kind of expressiveness. That's great. So, well, from a computational point, really, we could say the data flow approach is really functional approach, and I've motivated accounts is really object-oriented programming, or imperative object-oriented programming, which means you have the distributed concurrent data structure, and at the core of it, you use a big piece of mutable shared state. Does that sound like a good plan to you? But what about these smart contracts? I have to get back to smart contracts. Now, if we look at existing systems, then Bitcoin has this nice functional ledger, but there's basically no scripting ability in Bitcoin. Whereas the second biggest blockchain, it's called Ethereum, it has this account-based model, and it's really expressive as a full-blown programming language, and it's awesome. You can use millions that way, and people have. There have been hacks which has cost a lot of money for the people who got hacked. So great expressivity, but not so good with the safety. So one is very expressive, other is very nice and functional. Can we kind of bring the 2 together? So quite a few approaches these days, third-generation blockchains, look at using an actor model instead of a full-blown mutable state everybody's just writing to, as in Ethereum, like Concordium, Thesis, all these chains. We've been a bit more fundamentally functional and saying, can't we take this data flow graph and make it more expressive in the information which is flowing around and have a really functional system? So to see how this works, well, we have to understand a little bit more about how validation works in this data structure. So we have these bits which are called transactions. This is like the transaction of I pay you so-and-so many ADA. Now, if I want to spend, and we just said, the ability to spend one of these dangling black edges of the graph means I own those funds. How can I prove that I can spend those funds? So if I have a second transaction which wants to spend from the first one, making this link, then the check of whether that's permitted or not works as follows. So the output, the black edge, which I want to spend, has a value. That's how much cryptocurrency is being transferred, and a bit of code called a validator attached to it. And that bit of code is supposed to check where this connection can be made. And the spending transaction, the red bit, submits a redeemer, which is also a piece of code. And now the check is very simple in functional programming terms. The validator is a function we apply to the redeemer. If it evaluates to true, good to go. Very simple, very local, very easy to reason about. But because it's so local, it's not very expressive. That's why Bitcoin doesn't have a lot of scripting. So how can we make this a little bit more expressive? Well, we add a bit more information. So instead of just having the validator, we add a second piece of code representing some data structures or other code, and add that to the black outputs as well. And then we also take the entire information in the transaction, which we just want to check whether it's allowed to spend the funds, and pass all that along to the validator. So now the validator knows the redeemer. It has this additional data information, and it sees everything about the transaction and its outputs to check whether it wants to allow this, connection. And this turns out to be sufficient to have a much more expressive system. Why this thing with the additional data? Well, basically to give you the high-level idea, which to this audience I can explain in one sentence. Usually it's harder to explain to people. But we want to model these stateful systems by basically doing a CPS transform on the imperative program, getting a nice state passing functional program. That's the idea. So that's a slight extension. We call it the extended UTXO model. It turns out that we can express much more complex scripting situations. And it's still purely functional. And yesterday, Orestes Melkonian, he gave a talk about some work he'd done for his master's thesis at Utrecht University, where he had formalized this model in Actor. So one nice thing is, from using a functional approach, we immediately get a payoff, a really nice payoff. So this expression we have to evaluate to check whether we can make a connection, it's a purely functional expression, right? So we all know in this room, if you have a really functional expression, then when you execute these things twice with the same inputs, you always get the same output, right? But you don't only get the same result. Actually, execution will proceed in the same way. And for all the computations which run on the blockchain as part of validation, you have to pay for that execution to incentivize people to actually do the validation, build the chain. There's an execution fee. And that fee will always be the same. Now, you may say, being a functional programmer, yeah, of course, what's special about this? Well, what's special about this is that this is not the case for Ethereum. So on Stack Exchange, you find these questions. Oh, I submitted my transaction. I gave it a certain amount of execution fee called gas in Ethereum. And it just didn't work. And it ran too long. And can I get my money back? And the answer is, no, you can't get your money back. But you can try with more money, and maybe it works this time, or maybe not. So just not having this problem because we have a purely functional system is nice. So that's the ledger. That's how we have a purely functional ledger. So how about the code? I mean, I said we have to store that code on the chain. We have this immutable record of what's been happening, including some code we put in there, meaning we can't change it, no updates. So we'd better get this right? So what can we use as a representation for this code? So typically, our intermediate language is called Plutus Core. And typically, if you look at other blockchain projects, they use some kind of bytecode. for this immutable code you put on the chain. And still remember, I mean, this stuff, it protects a lot of money. This is the check to see whether we can make this connection. So we really want to get this right. And moving fast and breaking things is bad, because you can't unbreak them anymore. So typically, as I said, there's bytecodes being used for that, but we decided to use a purely functional calculus. And then that means we don't need a complicated virtual machine, which you also have to make sure does the right thing, because if that doesn't do the right thing, it doesn't help you if you know what your program should do if you only had implemented the virtual machine properly. But we use an abstract interpreter to interpret this calculus. And so we use something really old, and this really, like, Phil has pushed this. Like, we want to use a system, something that's been around for years and years and years, and has been studied to death, and we really understand it. So we are using system F omega with recursion. And it is a very small, old, very powerful system, lots of papers about it. Now, fewer papers than we thought. Because if you get to the little nitty-gritty details, especially if you add recursion, then suddenly it becomes quite a bit more exotic. It's really hard to find literature. But at least there is some. I mean, there's a lot to go on. And that's the basis for code execution in our system. Now, the good thing is a CEK machine for this calculus is quite short, and you can write a Haskell program which matches this quite closely. And again, then, we are in this situation where we have a specification, and it's quite easy to see that the Haskell code is following that specification. And to do even more, we had an actor expert, James Chapman, formalize this calculus in actor. And again, it sounds like, yeah, sure, that shouldn't be a problem. Like, everybody knows you can do that. But then sit down and try to do it. And then suddenly it's actually not that easy. So we have this formalization now. And we're in the process of also using to property-based test against the production implementation. And we also have a paper at MPC about this formalization. So, OK, functional ledger, functional code on the chain. How do we generate this code? We really didn't want to use Solidity. Solidity is the language of Ethereum. It's a weird Frankensteinian mix between Python and JavaScript. And you use it to protect millions. OK. So the second popular choice is, let's invent a new programming language. And I know what you feel like. I feel the same thing. Somebody comes to me, says, invent a new programming language. Yes, can I start now? But we all also know it's quite time consuming. And inventing new language is, I mean, the language part, that's like we know to do, we do over breakfast, we invent a new language. What's the problem, right? But you have to get the community, documentation, compilers, editor support, and then starts to become very resource intensive and time consuming. So we thought there's another programming language where people thought it's a bad idea to invent lots of different, very similar programming languages, and everybody has as different but somewhat similar language. Do you know it? It's called Haskell. And that language is quite expressive, powerful. There's a community. All this documentation is already written. There are compilers. Thanks, Simon. So let's just reuse this. How can we? The question is, can we reuse it? If we can reuse it and write contracts in it, that would be great. So what do these contracts look like? And I just want to run you through a simple example. So let's suppose we have a simple crowdfunding situation. This is like Hello World for blockchains. So I'm starting a project. I want to get some funding, like on Kickstarter, and get some people who invest in it. And then if I reach a certain funding goal, then I'm going to do it. Otherwise, you get your money back. So we have a payment deadline until which I want to fund this project. There's a certain goal I have to reach. And if it's not reached, there has to be a way to redistribute the funds which have been paid in. And otherwise, I, as the campaign owner, if I reach the goal, I can get the funds. Now, if you do this in Solidity, you're going to write some Solidity. That's painful. But what's worse is you're going to write even more JavaScript. Because Solidity is only about the on-chain code, and we've seen earlier we also need some off-chain code, and that typically people write in JavaScript. So then we get this strange setup, right? Like we have JavaScript code calling Solidity code. Calling means doing transactions over a socket using some random JSON format. And so really, looking at this, it looks like a two-level programming language, right? Done badly. And yeah, it's actually quite bad because it's inconvenient. Two languages. You have some code in one language, then you want to use this function in the other language, you have to rewrite it. And it's quite a complex interaction. If you change one, you change the solidity, change the number of arguments, the types. I mean, do you think you get a compile time error? No, you run the thing, it doesn't work. So we thought this is bad. So we use Haskell for the off-chain code. And then let's also use Haskell for the on-chain code. Well, we use a subset, which we call PlutusTX. And then, there's template Haskell to tie the two together. So let's use metaprogramming to have this two-level metaprogramming system. And that gives us an integrated, compact system where you write everything in one language, can put it into one program. And if I change one function and I forget to change the calling sites, I get a type error. Yeah, wonders. So how does this look like in Haskell? So this is just the function which I use if I want to contribute to this crowdfunding campaign. So I have a campaign I'm working with. I have some value of funds I want to contribute. Well, should be some positive value. Then I get my own public key from my wallet. Why? Because if the campaign is not successful, somebody has to pay me back what I paid in. And then I create a transaction which is locked by a script. So the situation we've seen. And what's in this script needs some code, and we'll have a look at that code in the contribution script in a second. But in this transaction, I only put the hash, cryptographic hash of the script, and the value I want to contribute. And then I put in as data. Remember, we extended this only value validator situation to value validator data script situation. As data script, I put the public key to which the refund should be paid if there's a refund being paid. And then I want to be notified if the campaign is successful or not successful once this has been decided, once the deadlines have passed. So I have a kind of callback. OK, so that's the code to do a contribution. And what's the code on the chain look like that determines whether I can spend from such a contribution? Well, a little bit more Haskell, but this time we wrap it into template Haskell. Because this is the on-chain program, which we have to compile to Plutus Core. And that gets the campaign an action, what I'm trying to do. Do I try to get a refund? Do I try to collect the campaign money? And the transaction. And we pattern match on the transaction, get some interesting information out of that. And then there are only two cases we have to consider. If I want to refund, then it has to be after the collection deadline, after the deadline for the owner of the campaign to take the funds out. Because maybe campaign was successful, but they ran away, and I still want a refund. And I have to pay the refund to myself, and the transaction has to be signed by my cryptographic identity, proving it's really me who tries to get a refund for myself. If all this is good, yeah, then we are done. But maybe I'm the campaign owner, and I want to collect all the funds because the campaign has been successful. Well, then should be after campaign deadline and before the collection deadline, and the funding has to be successful. So the amount of overall total funds needs to be bigger than what the goal was. And, well, I also have to cryptographically sign this transaction to prove I'm actually the campaign owner. And only in these two situations is it permitted to spend from these funds, from this contribution. So it's quite simple Boolean check, right? And in Haskell, quite compact, easy to see what it's doing. So if we have this program, what are we going to do? How do we go to use it on the blockchain? Well, we have a compiler which takes this, compiles it into code which runs in the wallet, which has embedded this little Plutus Core code snippets to put on the chain. And if I contribute 100 ADA, then my wallet will construct a transaction. My code, the code which I saw, constructs a transaction, submits it through the wallet to the chain, which validates it, and then the wallet also generally observes the chain and new transactions which are added, and this then leads to callbacks, such like the callback which we registered to if the deadline has passed, then check whether I get a refund or not. So we have this, and this goes around in circles. So that's the general interaction which we've got. Now, how can we implement this? We'll need a compiler for Plutus, and we need some execution environment. Now, with the compiler, we cheated a little. We just used GLC and added a plugin for the compilation to Plutus Core. Again, thanks, Simon. Saves a lot of work. So we basically use GLC to compile to GLC Core. And then we take this GLC Core in a plugin and compile it to an intermediate language, which we are calling Plutus IR. It still has recursion in it. And then that's finally compiled down to Plutus Core. And this is, again, one of these things where we thought, yeah, so we have Plutus Core system F omega, now data type definitions or something like that. And yeah, everybody knows Scott encodings, Church encodings. Of course, you can compile algebraic data types to that. We know that. We learned that in undergrad. Yeah, but then try to do it for actual Haskell core language, and then it's not so easy anymore. So there's another MPC paper where we have talked about how we approach this. So what about the execution environment? The Plutus is not yet on what's called the mainnet, the actual live blockchain of Cardano, because we are in a waiting line with other features which have to go in there. But what we've done instead, for the time being, we have implemented a fully functional simulator, what we call the mock chain of the ledger rules of Cardano. And we use this in a system we call the Playground. You can use it on command line, in tests and so on CI. But we also have a graphical environment, a web-based environment, where you can write your Plutus contracts and you can run them and you see what the impact on the chain is, and you can see whether a contract actually works and play through different scenarios of testing the contract and so on. And this is public. Everything we are doing is public in either research papers or open source software, but this you don't have to even build yourself. You can just go to this URL and use it. So overall, I hope I have given you a little bit of an idea that there is a huge overlap between ideas in the functional programming community and ideas which are really useful in the context of blockchains. And that because this is a domain where high assurance implementations are absolutely crucial, all our work on rigorous software development, semi-formal development methods, and formal development methods, and theorem proving, proof assistance, all is highly applicable to this area. And it's really only just getting started. So if you're looking for a new research project, there are tons of opportunities here. And with Plutus, we have designed and built a system where we try to do things in a quite different way than the typical JavaScript, Python-based approach of the old blockchains. And we have tried to use the kind of technology which come out of ICFP and apply it in a principled way to this problem of having smart contracts on top of Cardano. And to say it one more time, it's really, there are so many unsolved problems still in this domain, so many things which can be explored. We really have only seen the tip of the iceberg so far, so I think it would be wonderful if some of you would decide to also do some work in this area. Thank you very much.
Okay, well, good, Mike. So we'll start with one question from the Slido. So you said that a functional script will have the same execution fee every time, but then you said, so that's fine, but then you said predictable fee. So how do you actually predict?
So how do we predict this? It's a very simple solution. It's nothing tricky. We have this implementation of the whole infrastructure, which we also use in the mob chain. We can run the same code, the on-chain code, also off-chain, with the same inputs which it will receive once it's being used for validation on the blockchain. And we just execute the script in our abstract machine for Bluetooth Core and see how long it takes. And because next time you run it, when a validation node runs it, it takes the same number of steps in the same abstract machine. It's deterministic. So there's nothing difficult about it. It's just.
But in terms of predicting the time?
We predict the number of execution steps, which is what determines the fee.
But you have all the inputs at that stage.
Yes. That's in this particular model. The inputs are really just the transaction which is being validated, and that's exactly the transaction to which the script is attached. So we have this transaction, we are actually just constructing it, and we know the output from which we spend, because this already has to be on the chain, and because the chain is immutable, it can't change between now and the time where it's validated on the chain.
There's a couple questions over here. So actually, Adam had his hand up.
Phil wants to say something.
Well, it's worth adding a clarification to that, right? The reason it's worth adding a clarification to that. The reason that we know the exact input data, as Simon was asking about, is because we're using this functional model that you gave, the UTXO model. Under Ethereum, you don't know because you don't know the order in which the transactions are going to arrive and be executed. But with the UTXO model, each transaction says, I'm working on these 3 previous ones. So they have to already be there. You know those are the ones you're working from. The order in which things arrive doesn't matter. That's the huge difference between the account model that you mentioned and the UTXO model, and why the functional model is so much better. It lets you predict the inputs. In Ethereum, you've got everything else, but you can't predict exactly what the inputs are because you don't know what transactions have arrived first.
Precisely.
You described the benefits of building on an established functional language, Haskell, in the front here, and including static type checking. And then you decided to use explicit quotation of syntax for building contracts. When you can imagine, in a different language or even just a different implementation of Haskell, you could take normal Haskell closures and send them onto the blockchain. And it seems like you get much better static type checking support for constructing contracts programmatically in that style. So I'm wondering what made you choose to work with explicit quotation of syntax trees.
I'm not quite sure whether I understand your proposal. Is your proposal to, like Cloud Haskell, to take some runtime representation of the closures in a Haskell program and ship it to the chain?
Yes.
The problem is we have to, the code which goes onto the chain, it really has to be completely standalone because it's recorded on the chain. If some other node joins the system, the consensus system, it needs to be able to replay everything. So this really has to be, in something like Cloud Haskell, the code doesn't run in isolation, but all the nodes are being set up with the same libraries, the same everything, and then they can collaborate using Cloud Haskell. But here we have a situation where we need completely isolated code without any context. And so just using the existing closures, that wouldn't work.
Is it accurate to say that the approach that you have doesn't allow programmatic construction of contracts where you get a different contract at different points in runtime? Or at least you don't get good static checking if you do that?
You can construct data to a certain extent. So it's a 2-level system where we use the metaprogramming in Haskell, that's important for this, is compile-time metaprogramming system. It's not a runtime metaprogramming system where stuff is constructed at runtime. So in a compile-time metaprogramming system, all the metaprogramming code is also executed during the normal compilation run. Right? So this is all being done. All you can do at runtime is you can take this compiled, already generated Bluetooth Core and maybe combine two of these existing Bluetooth Core things. And the only other thing which we provide, and here we're getting into details, for the data strips, we have to have some way to take values, not computations, but values, and lift them into the Bluetooth Core representation at runtime. And this is basically works like the lift type class in template Haskell. So it doesn't work on function, it really only works on data.
Thanks.
Another question from Slido. Who is going to write these contract scripts? They're too complex for financial people. Do you foresee any high-level languages on top of Plutus?
Excellent question. Thank you, whoever you are. We don't only foresee a high-level language, we have a higher-level language, which I briefly mentioned. So there's Marlow, which is a domain-specific language for financial contracts, and it's based on the ICP 2000 work on financial contracts. It's basically the blockchain version, and we have a compiler from Marlow, from this domain-specific language to Plutus. So the way we see it is Plutus is really the general purpose programming system for Cardano for experts like in this room, people who are actual software developers. And on top of this, for particular domains such as finance, there is currently one, but there are going to be more domain-specific languages to make it easier for domain experts to access this.
Small question and a comment. The small comment, for F-star fans, there's also a blockchain called Zen Protocol, so if you like F-star, just want to add. And my actual question is, so you talked about ordering and validation, and also in your example, which is great that it's in Haskell, but I found it hard to follow who's actually the owner of the crowdfunding and who's participating, and it's a distributed system, so that I feel like session types would come naturally in here. Does anybody has followed up on that idea?
So I'm not aware whether anybody is currently building something using session types, but as I said a few times, this is really a new area, and we have tried to do like a very clear, very foundational functional programming approach towards writing these blockchain contracts, but it's not by far the case that this is it, we are done now. There are like a million things to do, and especially on the high level, when you look, I described this reactive event-based system between submitting transactions, getting feedback from the chain, and so on. This is not too hard to use for the kind of relatively simple contracts we've written so far, but it's also something which gets more complex, and we are using effect system to make sure this kind of is all under control, but I'm sure there are a lot of other great ideas which could be applied there, and session types may very well be one, and then Phil would probably be in a great position to yeah, talk to him. He's a session type expert.
Another question from Slido. How well do you cover the search space when you property-based test against your models?
Can I forward this question to John? No. So with property-based testing, of course, it's not a silver bullet. It's a really useful, extremely practical and effective tool, but you have to generate the right test data. If your generators are bad, then your testing will not be very comprehensive. There are, of course, ways like coverage checkers, but we go to a lot of effort to construct good testing data, which in particular means we actually have generators for blockchain blocks, where we generate particular sequence of blocks, which then needs to be validated in the same way by the two systems under testing. And we, of course, put a lot of effort into trying to generate chains which cover the search space as good as possible. But that's something which, yeah, I think there's no magic answer to this. That's work, and you have to make sure that you actually test how well you cover the search space.
Another? So Phil mentioned that the inputs will be known sort of at simulation time. If you have a large number of inputs, is it possible that they keep moving under your feet and you end up not being able to submit your transaction?
No, because as I said, so what Phil was referring to is which I didn't explain at all. So the way the Ethereum chain is constructed, an account doesn't just have a monetary value, but there's actually a global store, which is an association map, associated with every account address. And that is a globally mutable, always updatable data structure by other transactions. So if another transaction comes in, it could just change this global memory. And hence, you don't know what the state will be when it's your time to be validated. In our system, because the transaction, the function I showed was actually really, this is all there is in the system. It's the validator applied to the transaction, applied to the redeemer, applied to the data script. That's it. So we exactly know what arguments go in there, and the transaction, which is the most complicated part, this is what's being created by the code, which also attaches the script and does the execution. So the entity which runs the code and measures it is in full control of determining what the inputs are. So they can't just change by actions of other parties.
So one last question from Slido. Yeah, we're running out of time, so we're just going to take one last question from Slido. Why is the formal methods step separate from the research? Aren't formal methods part of the research? And a related question is, do you perform any formal validation, for example, in Coq of contracts?
So that's an excellent question. So why can't the cryptographers just write a Coq formalization of their protocols? And it would be beautiful, and maybe we are slowly trying to move towards a world where this is possible, but the cryptographers, they have their own way of doing things. They have their own strategies of how they write proofs about the systems. And it's just there's a huge gap in the way we approach formalization and the cryptographers approach it. And I don't want to be judgmental here. They're doing what they're doing for good reason. They're super smart people. They're doing highly complicated stuff, and they found the most effective tool for themselves to do their work. And that's why we have this gap at the moment. But I think there's ways to go forward. There is a certain approach, compositional approach, which is fairly new and is in high regard in the blockchain lab, towards formalizing these security proofs, security and safety proofs. And we are thinking about, and it's not just we, especially the people in Concordium, they are also really interested in how can we move this closer, how can we do these compositional cryptography proofs in Coq, and they've already started doing this. So hopefully over time this gap will shrink. But at the moment, that's how these things roll.
All right, let's thank Manuel.
Thank you very much.